In this video, we are going to talk about chips because everyone knows these are small components, but what is inside of these chips, how they are designed, and also what is so complicated about designing the chips. And Atchi is going to talk about this topic. Is this what we are going to talk about, Atchi?
Absolutely, Robert. Yes, I plan to take you, probably teleport you into an IC and then show you the intricacies of, okay, what's inside of it, and also share some of the complexities and also some of the interesting facts.
Okay, so maybe let's start about you a little bit. So you design chips or what do you do?
Okay, let's just step back. I did my master's in VLSI and embedded systems. It's VLSI stands for Very Large Scale Integrated Circuits. And after that, I joined IBM Microelectronics Division. So IBM is known for doing this large integrated circuits, large and complex and high performance. I've been with IBM SX groups for like 4.5 years or so before I'm moving to Marvell technology. And I've been with Marvel for last 14 years, 14 plus years. Yeah.
So you
And
know a lot about chips.
yes, yes. At Marvel, I was I would say I was lucky to work and also get exposed to various types of designs, storage, networking, and Wi-Fi designs. And I happen to lead the Marvel's first, I would say, machine learning or AI chip. It's a big chip. And I also recently happened to work on a CXL switch. And of course, currently the Marvel focused on this hyperscaler designs, which are huge, complex, complicated, and yeah, at the same time, they're very challenging and interesting. Yeah.
Okay,
So altogether, I have close to 2 decades of back-end chip design experience. Yeah.
I think many people who are watching my videos they know chips, but maybe not everyone knows what is exactly inside of the chip and how it is connected. So I would like to talk a little bit about this. So basically, from the pins of the
Hmm.
package,
Hmm.
how do we connect to okay, differently. So in the middle there is the silicon, yeah,
Yes, that's a silicon. Yes.
and then there are these bond wires. These are the
Yes.
okay.
Yes,
Can you show it
exactly.
with the mouse so everyone knows what we are talking
Yeah,
about?
let me try
No, no,
to.
you can just no, you
Oh,
can
I
use
can.
yeah, yeah.
You can see my mouse?
Yes, yes,
Yes.
I can see
Okay.
your mouse.
Okay, great. So this is the silicon.
Yeah.
Okay. Just to give you an idea, right? So this could be around like 4 millimeters on each
Mm-hmm.
side. Okay. Now, what you see, this color brown structure around the silicon is what we call a substrate. You can imagine this as a micro PCB,
Mm-hmm.
right? Now, the chip has this peripheral, which we call the IOs.
Mm-hmm.
Now, the IOs are connected to these traces on the substrate.
Mm-hmm.
Now, it is like you are fanning out these connections, okay, from this 4 millimeter square region to a much larger 15 millimeter square area,
Mm-hmm.
right? So that you can place it or connect it in a on a PCB.
Mm-hmm. I
So
think
you see the,
actually I
yeah.
think these are kind of standards. Yeah. I think when someone is designing chip, you can kind of
Mhm.
buy this package together with what we see there, and then you connect your silicon with these bond wires to this standard package.
We do have standard packages, and also we have several flavors of it based on the application,
Mm-hmm.
right? And the use case, okay? And also the performance of a chip also
Mm-hmm.
defines. For example, if you see here, this is the bond, wire bond, what we call
Mm-hmm.
connecting the silicon to the substrate, right? So this is a material. Now imagine that how thin it is, and then it has electrical properties and also thermal properties. Now, if you're designing a chip, whether it's say that's targeted for high performance. Now, the simple example is if you take this, what we call the SerDes, serial connections,
Mm-hmm.
though they run at a very high frequency in gigahertz, around like 200 gigahertz. It starts all the way from 10 gig, okay, then 30 gig, 64 gig, 112 gig, 256 gig, right? So the higher the performance, right? So the electrical characteristics comes into play as a bottlenecks. So what I'm showing here is the simple one, what we call is a wire bond,
Mm-hmm.
where the die connections are bonded with wires onto the substrate. We have other flavors of packages where the die will flip and then snap it, right, onto the substrate. So where we avoid these wire bonds, that has much better performance
Mm-hmm. You
characteristics.
can't just
Yeah.
solder it down.
Um, it's not the soldering, but it's a micro bump soldering.
Mm-hmm.
So that happened with high precision on say specialized equipment. Yeah.
Mm-hmm. Okay.
So that's called a flip chip, where
Flips.
you are, yes, you're having this die with this connection, small bumps, and then you just flip it onto the PCB.
Mm-hmm. I think I
You,
remember when
yeah.
I saw this for very first time, I was like, oh, I never expected that the chips are actually soldered upside down.
Oh, yeah, yeah. Those are called the surface mount, and then yeah, some applications they don't even have the package. So it all depends on the form factor. Now
Mm-hmm.
imagine that if I were to use the package, I need a 15 square of real estate. I would say here 15 millimeters on side. That would be like 225 millimeter square real estate. Okay. Now, if my application has a tiny form factor, right? You consider you have the optical links. We go into the data center, they have the optical links, and there is a chip in there, but it is the optical connection is pretty much as thin as your finger or something. It's like a cable, and then you go in, goes into the socket. Right? There, we don't have a room to have a package. Now, those cases where we just snap in the die and
Mm-hmm.
then with some protective epoxies, right? Yeah. So it depends, right, on the application and also on the performances, right? Um, Now, given that this, I mean, if we say that's an option, now why do we really have it for, or most of the chips has this, is for the protection, basically, right? So this is it's a thermal protection, right? And from any other hazards. So imagine having a bare die on a silicon. Then you have the hazards that we're going to discuss um, in later
Later.
slides.
Mm-hmm.
So I would say it is like a protection. Like right now, okay, we're in winter, and then it's cold. Like you and me are wearing a jacket, so to protect, right? So we have our jackets has a purpose to keep our body warm. Similarly, the package that you see here has a purpose to protect the silicon.
I remember when I was making one video, uh, we were talking about one of the possible problems, which was, for example, these bond wires they disconnected because of, I don't know, vibrations or something. And
Yeah, yeah,
so I wanted to point out this because problem maybe not only on the silicon. Sometimes if there is faulty chip, it may be even like bond wire can
absolutely,
break or
absolutely.
something.
That is an interesting topic. Is that right? So now take the analogy. Okay, if you have a software code as an embedded, it doesn't matter whether it's a high-level application programming or embedded programming. So software, we do have bugs, and then we have these breakpoints where we tap in, then we look at the values of different registers. Okay, try to debug what is going on, compare that what is expected. Now, we do have, like you pointed out, we do have some of those issues. Now, it is interesting that to learn more about those test structures, what we call, that we keep along with the functional structures in a silicon, so that the purpose of the test structures is to help debug if the functionality of the chip is not what is expected. So we do the same thing, that we probe these test structures and then tell them that, hey, go and then try read the value of so-and-so register, so-and-so element, and then let it know. Then we read it and then we compare with our standard expectations. Um, to give you a simple example here, just at the interface of these one buyers inside the silicon, we will have what we call a tapping points.
Mm-hmm.
Now we read those tapping points, and then those tapping points are all connected in daisy chain.
Mm-hmm.
Now, yes, like you pointed out, there could be an issue with the bonding wire. And if that is the case, that particular bit, we don't read any signal.
Mm-hmm.
Exactly, right? So
And
now you pass a pattern, and then you know, like, okay, how many bits or you're sending, and then how many bits you're reading, and then what is the expected value.
oh, that's one of the reasons, for example, why JTAG exists.
Exactly, yeah. So I'm glad you brought up this JTAG. Yes, JTAG is, I would say, a good analogy would be that it's an endoscope. JTAG interface is an endoscope to diagnose into the chip. Yeah.
Mm-hmm.
So we have that standard interface, and we send data and we send clock, and okay, we send a pulse of data. We wait for a certain time for the chip to digest it and then produce the result, and then we read it. Yeah,
This is very interesting
exactly.
because I always only thought about JTAG for board testing, used for board testing, but actually
Yes,
it can be used for silicon testing because, as you
yes,
said, you actually have access not to the pins which are on the package, but you are accessing the uh, pins which are on this silicon, which are on this die.
yes. So on top of JTAG, we also have additional structures because by see the fundamentally JTAG helps if, first of all, right, if there is a some defect with the manufacturing, or say a bound wire is broken, right? So in those cases, because it's fundamentally not a good silicon, right? So JTAG may not be of a good help,
Mm-hmm.
but similar like JTAG, so we do have what we call a scan-in.
Mm-hmm.
So yeah, some of those structures. Um, we do have controls where we want to put the silicon in a functional mode
Mm-hmm.
or in a test mode.
Mm-hmm.
So imagine like it's a switch.
Mm-hmm.
Now, when we turn on the switch into the test mode, right, now you get all those structures in the silicon are active for you to, okay, when you feed in data and then they take it inside the chip the way you programmed it, both logically and also through the I mean, not software to be perfect, but yeah, it's a little, I would say, uh, hardwire structures, and it's like a pipe for you. Okay, you feed in, and then with the power on, and then now the data comes out on the other end of the pipe.
Mm-hmm.
You start reading it. Yeah.
You started interesting topic because I know now we are not talking exactly about what you have in these slides, but I remember again talking to someone on this topic and realizing how much hardware and software is actually behind what people are expecting is on the chip, but there is actually much more stuff. So your chip is doing this, but there is much more stuff which people never see what is there, kind of configurations and I don't know what everything else, testing and this stuff. So chips are actually much more complicated than just what they are doing.
Oh, definitely, definitely. And to give you a perspective, right? So when we are designing chips, okay, the features that we want to include, because typically chip designing on average takes like 2 years or so.
Mm-hmm.
Now, if you find a bug, then that's another 1 year of cycle
Mm-hmm.
to get the silicon back.
Mm-hmm.
Okay, you identify the bug and then fix it and then send it to the fab and bring it back. It takes around 8 to 12 months.
Mm-hmm.
Okay, um, so this 2 years designing plus an additional 1 year of what we call the time for production. Okay, that's when I'd say any of the embedded programmers or anyone who sees the chip, right? And then you guys start playing with that, okay, feeding in code and stuff and all. Now, coming back to the chip design, the functionality that goes in, we actually plan out for several years,
Mm-hmm.
in cases almost a decade ahead. Okay. Um, yeah, obviously, right? So yes, because if you go look at the mainstream applications, right? So how many of applications are really using, I would say, USB 3 or PCIe Gen 5 or Gen 6, right? Not many, because right now, currently, what we are designing or using these interfaces, right? The DDR5, so DDR6 or Wi-Fi 5, 6, okay, and also the PCIe Gen 6 and PCIe Gen 5. You will see, I mean, I would say the products using these protocols or features maybe way out. I mean, you might see here and there a couple of them, maybe high performance or niche areas, but the general availability where you see many of the products using this high performance and then high throughput interfaces, maybe another, I don't know, 7, 8 years away, right? So that's how usually the amount of logic goes in the IC, I would say the silicon, as yes, it is much more than what you might see or access from a software point of view. Because the reason is that the development cycles are longer, software, I think, relatively shorter. With all due respect, I understand software makes it very easy, say, ease of use for the customers, right? For general, even I am a consumer of a product, several electronic products, and I prefer ease of use, and that is possible with the software, right? We can program, reconfigure, yeah. But if I were to do, and if I'm expecting the same to do with the silicon, the cycles are longer. So that's the reason why we have to plan, okay, ahead of market, think, okay, which way the market is going through, the products are leaning to, before we design a chip.
Mm-hmm. And of course, it's expensive. It takes a long time,
It is
just to make
expensive.
it. So you need to
Yeah.
be double sure that if something doesn't work, something will still work.
Yes, it is. Yeah. I mean, this is the general, say, information available out there. I mean, if you hear from NVIDIA or those guys, they are designing the advanced, I would say, um, GPUs, and they are in the advanced process nodes. For them, each chip costs close to like 600 to 700 million, just to get it fabricated. Yeah.
Million, six hundred
Yes,
thousand to million, just
600 million,
six
not
hundred million
600,000. Yes, yes, it is. Yeah.
to
I'll,
design
I'll,
one
I'll
chip,
show you.
specific chip.
Yeah, yeah, yeah. I'll show you in one of the slide. I gave a comparison that a normal human hair thickness is around 75,000 nanometers. Uh, those, I would say, the wires inside the silicon that we use to connect these different transistors, they are 20 nanometers thickness. So that's almost like 3,000 times smaller than a human hair.
Uh, okay, so let's move to the
Yeah,
beginning
let
of
me
your
let me yeah, go
slides.
to quickly go to the next
Oh,
slide
next
and
now.
then
Okay.
show you here.
Oh, okay. This
Yes,
is what you mean. This is what is.
exactly. Yeah. I mean, this all looks nice, good, I mean, nice grade, right? But then to reach to that view, you need to have a microscopic X-ray with a powerful lens. Okay, yeah. So this is how the structures inside of it. I mean, yeah.
Okay.
If you guys are following this Ant-Man and then the next version of Ant-Man where they were talking about the quantum realm, okay, where he wants to miniaturize to the size compared to of atoms, right? Assume, okay, if you could do that yourself, and then if you can enter into a chip, okay, so this is the structure that you most likely see. It looks like a nice maze, whatever we write, a corn maze or any other hay maze that we see during the holidays. Yeah. But then that's reality. Yeah.
Okay, so when you started this, maybe we don't need to jump at the beginning, but maybe we can talk about why is it so difficult to design the chips. And I know you mentioned to me before when we were talking about there is, for example, even like keeping in mind uh, what is going to be ambient temperature of the chips is super important, because you can design the chip for 20 degrees, or I don't know how much Fahrenheit it is,
Yeah.
or yeah, room temperature, and suddenly the temperature will change, and the behavior of these very small structures can also change, and it can be influenced just by temperature.
Okay. So before we dive into that, right? Or maybe let me explain this. Okay. Now we established the base, like the structures I told you is 20 nanometers, right? So that is pretty close to atomic structure, which is an Armstrong's. Sorry, Armstrong's. Um, Now these are all basically the chips are made from I would say grown on a silicon. So silicon is a material, right? And if you are fabricating a structure, let's say the transistor is nothing but a switch. Okay. Now, sorry. So imagine a switch, just like on-off switch, and that is as small as, like I said, it's 20 nanometer or something. Okay. Now it is a material and it has electrical and also thermal properties. We all know that, I mean, if you take any concrete bridge or the roads, right, we have these blocks of concrete slabs that they put with some gap
Hmm.
to allow the expansion during the summer.
Pipes, for example,
Yeah, exactly. Yeah, even the
even
pipes, you
even
take any of
electrical
the metal
wires.
structure. Yes, electrical wires. So they sag, right? In summer. So it does happen even to the material or silicon, right? So when the temperature raises, okay, and it also has this, they have the electrical characteristics, and now the switch can turn on because of its low threshold. I mean, we apply the voltage, and then there is a minimum voltage that needs for the transistor to turn on to enter switch. Now, because of the electrical properties of the material, the barrier is now shrinks. It gets lower. So even with a small variation of the voltage, the transistor will turn on. So that is an unintentional switch on of the circuit, right? So it is very, very important that when you fabricate it, even if there are a couple more atoms, say thicker than what we expect or less thicker than what we expect, that will play an important role in defining the characteristics of the switch.
Hmm.
Now, along with that, now there is a temperature variations, right? So there will be unintentional behavior, circuit behavior that makes it really challenging. So going back, that's what happens if you take this device to a place where the temperature is higher than what is expected, or uh, higher than the spec of this particular chip, then you expect unexpected behavior. Yeah.
Hmm. Are there some other difficulties? So it is very small. Then you have to be careful about temperature.
Yes,
What
so
else is
so that
there?
is a temperature, and now the another thing what we say is that the reliability
Mm-hmm.
is that okay, I design it, now how long I can use it or how long I can
Oh,
operate it.
it
Okay,
can
yeah, that
expire. Chips can expire.
um, well, to put it simple, yes, but to explain that now, you start using this, okay? Of course, there is a wear and tear, just like mechanical parts, even electronics has wear and tear. And the wear and tear, in a sense, is that the device gets damaged because of these charges. I mean, when I say damage, it could be some of the wire structures you see here, right? So pretend this is a pipe and then water pipe, and then you are using it for several years, okay, where we see the deposits happening. So the higher the deposits, what happens? It narrows down the cross section of the tube.
Oh, really? This is really like electrons will leak
Yeah,
off or
yeah,
something?
yeah,
I don't
yeah,
know.
exactly, exactly. So that becomes that's one case, and it's where it can happen in either way, right? So if there are some electrons accumulating at one place, that means there's another place where you are losing those electrons
Mm-hmm.
or atoms, right? So where the atoms are migrating, it's a migration problem. That's what we call electromigration. That means just like the birds migrate or people migrate, electrons do migrate. Okay, so then you wherever it migrating from, it becomes an empty space. It's called open. Now there is no path, then you don't see the signal passing through. And then where it is accumulating, now there is a neighboring tracks, and usually their spacings are very thin.
Mm-hmm.
Now what happens if it bulges,
Short
it goes
circuit.
and then yeah, short circuit. So
So they can
yeah, if you call
break or
that
they
as
can
expert,
make short
they can,
circuit.
yes,
Mm-hmm.
yes.
Huh.
So these things can happen. Yeah. So now this makes it what we call is a reliability that could happen anytime during the fabrication or when you are using the device.
Mm-hmm.
Okay, if it happens during the fabrication, with several factors that could impact a good die or a bad die. So that's what we call a yield. I mean, if I am say fabricating 1,000 chips, maybe 70% of them turns out to be good ones, and 30% we may lose for
Mm-hmm.
various reasons. Similarly, okay, now I got 70 of the good ones. Now, how long can I use all of them, right? So we expect all of them last for, let's say, for example, 10 years,
Mm-hmm.
15 years, right? So yeah, that's another problem. Yeah.
Mm-hmm.
So when we design, we stress these conditions to ensure that um, the silicon or the circuit uh, perform as we expected under these uh, conditions.
So now I'm curious. Does it mean smaller and smaller technology is used? It is there is higher chance that the chip will stop working sooner.
Um, let's put it in another way. Is that okay? Uh, the smaller we what we call it the feature size or the process node, the smaller the feature size, you better be more cautious
Mm-hmm.
to ensure that it works as expected.
Mm-hmm.
You need to have more simulations done or okay, more checks and then try to simulate, right? So, and then foresee all the different combinations. Okay, what could happen? Okay, some of the older process nodes, let's say 20 years ago, may not have these stringent requirements when
Mm-hmm.
we design. Okay, for example, you see here, right? Maybe in older technologies, oh, is a long line, sorry, a long wire here. There is a neighboring wire. We just need some spacing. That
Mm-hmm.
could be a requirement. Now, when we reduce the feature size, okay, then we shrink the size. Now we need to take care of. You see this little notch here,
Mm-hmm.
where I'm pointing, right? So even that could be a significant influence in terms of the performance. Because what we call is crosstalk, as the signal that's running in one electrical wire can influence, just like an electromagnetic effect.
Yeah,
Okay, it can influence the neighboring wires or the structures.
can
So
generate
now
noise
all
in
these,
different.
yeah, exactly, noise. Now the device, the transistor needs to be robust enough, okay, to I would say isolate or identify these situations, right? Yeah. So that's where you see that the I would say the more that you shrink, now you tend to run more checks to ensure, okay, what are the limits.
So are the simulations really so good? They consider everything, or I'm just
Yes,
curious.
it's yeah, your simulation is as good as the model, right? Yeah, just
Ah,
like so now um, how big your model is in terms of okay, how many factors you are considering, right? Yeah. So there is material coefficients, and there is a thermal coefficients, and you add in additional reliability coefficients. Yeah.
mm-hmm,
And also you add in any of those fluid dynamics related coefficients, right? So
mm-hmm,
consider this small particle, right? So this could happen at uh, wiring or inside the device. Yeah.
mm-hmm. Okay, I understand. So basically, when you design chip and you run simulations, you not only run simulations once for one situation, but you run simulations even for
Yes.
the limited uh,
Exactly. Yeah.
values of not only one thing like temperature, but limiting values for
Yes. We have
manufacturing
several
process or
parameters. Yes.
and for
For
crosstalk. And
manufacturing,
uh,
crosstalk, even if you look at it is, I mean, made out of basic building block is a CMOS transistor. Now the CMOS transistor has two structures, so what we call a PMOS and the NMOS. Okay, each one has a their own doping levels. So yeah, we do consider, okay, what is the doping levels? Okay, and what is the spread? Okay, what is the coupling capacitance between those devices and the structures based on the area, thickness, and the width? Yes, they all play important role.
okay, I think now we can have a look inside of the chip, like how it is, how these transistors are, for example, designed. I think you have some slides
Yeah,
here.
so let's, okay, I'll switch
Yeah,
to
yeah,
the
this,
next
yeah,
slide.
exactly. This is
Yeah.
what I mean.
Um, so this is how you would see, like I earlier I mentioned, right? If you are in Ant-Man quantum realm, okay, and then you are inside the chip, okay, this is the mega structure that you would see, right? But then from a human point of view, like I showed you here, so this is what we call VSS. It's a ground rail. Um, Usually you'll also have these ground rails on your PCBs, right? So we do have them inside the chip. And this is 20 nanometer thickness. I mean, say the width.
Mm-hmm,
So it's a three-dimensional structure. We do have the length and width and the height.
mm-hmm,
Yeah. So, but this typical dimension is 20 nanometers.
mm-hmm.
Yeah. To compare to human hair, it's like 75,000 nanometers. Okay. But now coming back, so you see a big blue, what they call the block here.
Mm-hmm.
So this is the silicon.
Mm-hmm. That's the
Um,
base.
it's it, it's a base, yeah, and we call wafer. So
Mm-hmm.
it's a circular.
Mm-hmm.
It's around. There are several flavors of it, like 200 diameter, 300 diameter. So it's pure silicon, and on this silicon, based on the type of device, active device that we want, either PMOS or NMOS, so they inject ions to make it as a P-type material or it's an N-type material.
Mm-hmm.
So the N-type material will have a semiconductor is they have valency of 4 in the outer, I would say, outer shell of an atom. There are 4 electrons. Uh, so the N-type material will have 5 p-type material will have 3. So because of the imbalance, we can, with an additional supply, we can control the flow of electrons. So that's a basic operation. Now,
But you apply some kind of mask, and then
yes,
you apply some kind of chemical process
yes, yes.
which will, I
So
don't know, add or
yeah, we
remove
put a
the
mask. Let's
something.
say I want to grow a PMOS transistor here. So I'll put a mask where I expose this part of the base,
Mm-hmm.
and then I cover rest of it,
Mm-hmm.
and then I start injecting
Mm-hmm.
ions,
Mm-hmm.
and then only in that opening area where
Mm-hmm.
the ions will go and then sit, make it the material as more P-type or N-type.
Mm-hmm.
Okay, and now I remove that. I have this now big transistor, but I only need a contact at one particular place. Okay, now I put another mask where I have an opening where I want the contact is.
Mm-hmm.
These are the contacts. You see
Mm-hmm.
the brown ones. Okay, and then I cover rest of it, and then I fill in the epoxy material, not epoxy material, but uh, and then I fill it with whatever. We have different types of material that we use for these contacts. Cobalt is one option.
Mm-hmm.
Now, recently, they are also switching to tungsten because of the electrical properties. Now, I go up. So this
Oh,
is
okay.
where the metal
Before
layers.
before we continue, so you cover the whole layer with some kind of isolation, which makes isolation between different layers, and you only make holes where you would like to have contacts going up.
Yes.
Okay.
Yeah. Um, yeah, we fill in the material and then we polish it and then put another layer of mask and then
Mm-hmm.
again fill in material and then we polish. Yeah,
Mm-hmm.
so that's what we do. We build layer
Mm-hmm.
by layer, level by level.
Okay, and you can. I think there are few things what I remember again from previous videos. So you go from like smallest things to the biggest ones, or that's how it works.
We go from the bottom to the
Yeah,
top.
yeah. But
Uh,
on the bottom there are the smallest structures, and then going up, up, up.
yes, the at the bottom are thinner structures, and we go up, we use thicker structures.
Mm-hmm.
And the reason is at the lowest level where the active devices, the transistors are. And we're trying to squeeze more transistors per square inch. And we could do that by shrinking the size of the transistor. So every new process node, the transistor size is shrinking. So we need to have a thin structures to establish the contacts. So now on the lower level, we do have this narrow structures. Okay, which is good, but nothing comes for free. So the thin structures, they have, I would say, pessimistic electrical characteristics. The thinner the the wire is, the more resistive it is.
Mm-hmm.
Because assume it's a narrow water pipe to a big water pipe. Now you could only have a limited amount of water flowing through a narrow tube compared to a wider tube. So it's the same thing here. And coming to the performance, okay, some of the signals, okay, if it has to go from transistor to transistor B within a certain time, let's say if my device is doing operations at, let's say, 1 gigahertz per second, now I want to have this operation done and then send data from one part of the chip to another part within, I would say, a nanosecond. So I definitely need a conduit which has a better electrical
Mm-hmm.
characteristics. So if I rely on these thin structures, then I may not meet the performance. So I need structures which are which have a good electrical characteristics. So that's the reason why we, as we go up, we try to use the higher structures because there is no, not the higher. The higher we go, we use the wider structures
Mm-hmm.
because there is no reason for them to be thinner because they are far away from the device in a vertical direction and they have a better electrical characteristics. Yeah, we use that and then like to the point B.
Mm-hmm. And so can you have more copper layers?
Yes, I have a picture in another slide where I can show you, but that context is a little different. Yes, we do have additional layers. What I'm showing you here is that, um, this is the top
Before
one
I
here
forget,
is the
I'm
pink.
sorry
Yeah.
for interrupting. So basically, if I understand, or maybe I may be wrong, you can build the components only where the silicon is, and everything else is kind of connection, or
Sorry, everything else is?
are the connections, or can you build components also on the other layers?
No, components basically they lie at the base
Mm-hmm.
structure. So what we call components are nothing but the transistors.
Mm-hmm.
Those are active devices.
Mm-hmm.
So they stay at the lower layer. At the higher layers, it's all is the metal
Mm-hmm.
wiring connections. Yes.
But this can create capacitors and resistors or something like this.
Capacitors, the active capacitors, they're still on the lower layers.
Oh.
Um, but we can use the higher layers for capacitance or inductance just purely based on their metrics, right?
Mm-hmm.
So if you put two wide sheets next to each other, that is a capacitor
Mm-hmm.
by nature of its properties. Similarly, you have a conductor and then you go around in circles, that forms a inductor.
Mm-hmm. Okay, so
Yeah,
this is
those
interesting.
structures, yeah,
This
yeah,
is interesting. So basically, all the other layers are only kind of metallic layers.
metal, yes,
Mm-hmm.
yes, yeah.
Okay. Okay, I think
And now,
maybe we don't need to go too much into details
okay.
here. I think we explain. So you mentioned you have a different picture.
Oh, yeah. So, okay. Maybe I can bring
Oh,
it in.
okay. So, so how many layers you can put there?
Um, we can go up to like 15, 16 layers.
Wow.
Yeah. So you see this here on the bottom side where I'm pointing my cursor.
Mm-hmm.
This is the base where we
Mm-hmm.
have the active devices like transistors.
Mm-hmm.
And then immediately on top of that, what we call the first layer of routing.
Mm-hmm.
And then you have second layer. And these alternate layers, they run in orthogonal directions. If the first level is running in horizontal, the level
Mm-hmm.
above will run in vertical.
Mm-hmm.
It's like in Manhattan directions. And the next level above is again horizontal, vertical, horizontal, vertical. So any connections that you see on a silicon, point A to point B, they are either go horizontal or vertical.
Mm-hmm.
And the reason is that if you tend to take 45 degrees orthogonal, like I explained earlier, so there is some manufacturing or fabrication challenges, okay, and your yield will go low. So
Mm-hmm.
for that reasons, we want to stay with, okay, orthogonal structures.
Mm-hmm. So if
And
you
you
make
see,
like routing like this on one of these layers, then it can break where the corner is or something.
yes, exactly.
Mm-hmm.
You take 45 degrees, right? Now that may not be strong enough,
Mm-hmm.
okay, connection there. It
Oh,
depends, right?
I
So
didn't know
yeah.
this. I didn't know this. That's
Yeah,
interesting.
and PBC and in PCB you can take 45 degrees.
Yeah.
Yeah, because it's thicker enough. It has a good electrical properties still there. Yeah. Now, if we try to do the same thing, but we do we do have 45-degree structures on the top metal layers,
Mm-hmm.
but definitely not on the lower metal layers.
Mm-hmm.
So we only do that on the very top metal layer.
Mm-hmm.
Yeah.
Here I can very nicely see like it's bigger and bigger and bigger and bigger.
Yes. Yes.
So the top layers, I guess there will be mostly for like power distribution or something.
Yes. Power and if you remember those wire bonds,
Mm-hmm.
right? So from the wire bond connection to the actual device is
Mm-hmm.
we call the pads.
Mm-hmm.
Yeah,
Mm-hmm.
for those I/O connections and for the power distribution.
Mm-hmm.
Yes.
Okay. So why did you create this routing congestion?
Or to congestion, right?
Yeah.
So yeah, I mean, like I mentioned earlier, right? So typical integrated circuit, even if you take 100 mm square by 100 mm square, you will see the billion of transistors, right? And one would wonder that, okay, what are the challenges in putting, you can just, it's not just you can just cram them into one place, right? You also need to think about connecting them, okay? And of course, the routing is also a challenge. Now, if you compare that to a typical metropolitan city, right, where every day we commute, we come across this traffic congestions. Okay, now imagine, okay, now all our vehicles they go on land, pretty much for commute that we use. Of course, we do have airplanes for long distance travels. Now, imagine if your cars or buses can fly, what would that look like in terms of commute, right? And also how to handle the traffic or congestion. You may not have that option right now in real life. Maybe in future there are people talking about coming up with this flying cars. Um, of course, we see them in our scientific fiction movies, right? Yeah. Fortunately, in chip design, right? Though we brag about, hey, we pack complex things into tiny areas, but we do that with using this multi-level, multi-layer routing connections. So the possibility of doing that is a blessing, right? So that it enables us to pack so much complex things
Mm-hmm.
in a tiny area, and in turn reduce the form factor of any of the electronic devices that we use
Mm-hmm.
today. Yeah.
Okay, I understand. So basically, you created this slide just to point out that we really need multiple levels of
Yes.
connections.
Yes.
Okay, what do you have
Yeah.
on the next one? Oh, there are the operating conditions. We were
Operating
talking about the
conditions.
temperatures.
Yes. Yeah. So this is the temperatures that I described earlier. I'm in US. You are also familiar, right, with the US. The US itself has 3 time zones. And if you see from east to west, they're apart by 3 hours. So that gives you an impression, right, how wide it is, and of course the temperature conditions as well. The north you go, it's colder. The south you go, it's hotter. Now, if I'm designing, let's say, a phone or any other electronic device, which in turn uses this integrated circuits, right? Um, okay, I'm in California. Okay, I have nice warm weather. I design a chip. It works perfectly fine. California. What if you go to Alaska, or you go to Maine, or you go to Arizona, you go to Florida, you go to Texas? Will it uh, give similar performance, right? Yeah, it will unless I take care of those conditions when I'm designing it. Yeah.
Mm-hmm.
What we do is that, okay, we do for the typical conditions. Now we do a stress test with this, I'd say, extreme conditions to see, again, this is another simulations that we do to see, hey, what kind of fails that we are seeing. Now, how do we take care of those things so
Mm-hmm.
that when this device is operated in those conditions, it still performs as expected?
Mm-hmm.
I'm not sure if you ever got a chance to see a message in your phone, which is on the top left corner of the slide. That's simple. What you can do is that you can leave your phone in your patio or in your backyard somewhere in the sun for 10 minutes or so. It gets the temperature goes up of the device, and you will see a message something like this. Hey, your phone temperature is high. It needs to be cooled down. Okay.
I
So,
see, once I was recording in PCB manufacturing company, JLC PCB. We went to the room with the ovens where the
I
PCBs
see.
are baked together, all the layers are baked
Yes.
together.
Yes.
And just in the room, there was like 40 something degrees, and I started recording, and after 10 minutes, I had this on my screen.
So, see, like I said, right? So earlier you pointed out it's not just the functionality. There's so many other things that goes into the chip, right? Yes, this is one of the things. So we do have sensors, sensor circuits, I would say,
Mm-hmm.
in the chip. Okay,
Mm-hmm.
they sense and then they give send signals. So yeah, which are read by the software,
Mm-hmm.
and then yeah, in turn they configure the operations. They say that okay,
Mm. So
yeah,
basically, you can
so
kind of dynamically, maybe based on the
exactly.
temperature, kind of control some properties of the some specific areas in the chip or something, or functions of the chip.
Yes, yes,
Mm-hmm.
exactly. Yeah, and also not just the operating or weather conditions, but it also depends on the type of application that being run. So there are certain portions of the chip, okay, they are active, the others are quiet to
Mm-hmm.
conserve the power.
Mm-hmm.
Yeah, so that's another advantage. All these things are taken care by software. That's the reason why initially I said that yes, software is important and very, very important. Yeah,
But this is the software what we are talking about is the software which is kind of running on the silicon and no one
on the
ever see it.
silicon, right? Exactly. Uh, Mostly the embedded guys might aware of that.
Is it the microcode or
At
something?
Yeah, yeah, it's close to somewhere microcode. I mean,
Ah,
they don't
okay.
have to. Yeah, they don't have to code. Usually, any company that's designing these chips, they also provide this. I would say a basic code. Yeah, they provide that. At least the hardware
Mm.
interface. Yes.
Ah.
All, I mean, for you, it's only a controls saying that, hey, if this bit is on and then, okay, do this or not do this. But yeah, from the raw hardware, the signal coming from the raw hardware to the configuration settings that an embedded engineer or any high-level programmer sees. So that's the bridge.
Hmm.
Yeah,
So
so
now,
that's the small piece of code that makes the chip alive. Yes.
now I have a question about sensitive topic. Like,
Hmm.
is this one of the reasons, for example, why some countries may be worried what exactly is running on the silicon because there can be code which no one knows what is actually running on the silicon?
You're right. You're absolutely
Ah,
right.
okay.
Yes. Yeah. Yeah.
Uh,
I don't want to go into
yeah,
those
we don't need to go.
details,
I
but
just.
yeah, that's a possible. No, it is possible.
Hmm.
Because like you pointed out earlier, right? So you have the JTAG interface.
Hmm.
Yeah, you can hook it up to JTAG interface and then you can start injecting the code.
Hmm. Okay. What do you have on the next slide?
Next slide is about the
Oh,
ESD.
we never mentioned this one, but I've seen so many problems with ESD. So this is one of
Yeah.
the when I was starting with electronics, so many chips they were gone like this because of I don't know. I just touched them by hand. Then
Yes.
it improved, but
Yeah. See, the simple analogy is that, right? I mean, we talked about it. You put two sheets of metal together, that becomes a capacitor. Okay. Now imagine a human body, right? So we have a large surface area. Let's say humans have large surface area based on their size. Okay. Imagine how much charge that we could accumulate. So it could typically somewhere around 3,500 volts to 35,000 volts. So that's the amount of charge that we could accumulate based on the conditions. Okay. Now, when you touch a chip on a PCB or anywhere else, right? That discharges through the chip. Now, these chips are designed to operate at a very, very low voltage, around 0.75 volts, less than 1 volt. Now, that is their normal operating range. Now, if you are discharging all of a sudden this large voltage through the circuit, and then we talked about, right, how teeny those structures are. Yes, most likely there will be
Jump
some one or
between.
more structures, yes, yeah, get damaged, right? Yeah. Now this is a big topic, right? Yeah, we do hit most of the time, and we also need to have a production circuits to take care of this. And the simple analogy would be that what we have is the bypass structures. So there is active device, and we try to get this bypass structure, which is low resistance,
Mm-hmm.
just like a circuit breaker,
Mm-hmm.
what you have, right? So, and sometimes we have these diodes,
Mm-hmm.
what we call this, like a Zener diode is the best example. Yeah. So what we call these are the clamps. Now, whenever you have this high voltage applied, now I have this clamp which is parallel to my active device. So irrespective of what voltage you apply, now this clamp will limit the voltage
Mm-hmm.
that the active device sees.
Mm-hmm.
So now the device is protected. Yeah. And this is most likely the first failure that we may see, because there might be a case where we miss some of those signals which are not protected, or devices which are not protected, right, for whatever reasons. Yeah.
Mm-hmm.
We do run these simulations, and we do verify this. We have dedicated checks uh, for ESDs,
Mm-hmm.
but still there might be cases where here and there. Yeah. And here you see is how the failure would look like in a silicon.
Mm-hmm.
Again, if you wear your microscopic X-ray lens, and this is how you would see it. So this is the metal structure here, and you see there's a damage. It's like either bulging and then becoming open and then shorting into the neighboring structures.
Mm-hmm.
So yeah,
Okay, so basically this is what helped. Just or I guess when chip companies started designing these chips, and all the chips were failing, then these chip companies, they started taking care of these ESD, and
yes,
they were
yeah,
very serious, because I remember, again, it was between the times when everyone was failing because of ESD, and then it started getting better. I remember, in your lab, you're supposed to have everything ESD connected, or ESD discharge connected and something. And I was always like, no, I'm
you
not
need to
going to
have
do
that
that.
on
Yeah,
your
I'm not
wrist.
going to do
Yes,
that, because I would like to find out if there is a sensitive chip rather than my customers. So,
exactly.
of course, you have to use it in production, or in, yeah, when the chips or boards are manufactured. But when I was working in my lab with new boards, what I was designing, I was not wearing this stuff, because I wanted to find out if there is something sensitive.
No, they are sensitive. Yeah, you don't want to try that unless you want to. You don't see it, but then you're burning chips, yeah, inside of it. Yeah.
Yeah, but then I knew, oh, this chip is too sensitive, I'm not going to use it, so I remove it from BOM and I use something else.
Okay. Okay. Yeah.
Uh, there was something else what I wanted to mention. This is something what many people don't realize, actually. And when they are designing boards, for example,
Yes.
they forget that pins are actually connected through these diodes, and
Yeah.
in some conditions this can be problems. For example, when part of your circuit is powered and the other part of the circuit is not powered, and you are sending out some voltages through signals, they can actually go through these diodes and
Yes.
power the
Yes.
unpowered part of the board.
They
And
do. They do. Yeah. I mean, see, in this case, like you said, yes, it doesn't need to be power, right? So you take a bare silicon, bare chip, and then you try to touch it, right? Yeah. So you might have realized that even when they they were shipped in an electrostatic
yeah,
protection sheet, right? And the covers, the bags. Yeah.
I
So
I, I
this
have.
is silly. I mean, it sounds very silly that what touch and then I see it gets damaged. But yes, it is. It is very crucial. Yes.
Yeah, and when we are talking about this, I have kind of funny story. When I remember I was testing one chip, and I left it I don't know exactly how I was testing it, but I think I put it on the on the black stuff, which usually is shipped with chips. You plug in the chips on this electrostatic something material,
Yeah,
and I put board on this, and the
I see.
board was was like behavior was really very weird, and I was like, well, what's going on? And oh, okay, I guess that's conductive.
Yeah, yeah, that's true. I mean, it is funny when we look back. Yeah, but yeah, these are all the possibilities. That makes it really interesting. Yeah.
Yeah, I wanted to mention this because
When
maybe some people they don't realize like, oh, okay, when you are testing boards, maybe don't place them on these kind of materials because
yeah,
you can get all the kind of different behavior.
was during my early phase of my career, I was thinking that okay, maybe getting the right performance and then getting the optimal size, they're much more challenging. But then when I get to know of this, okay, I design the chip, and then what happens? Then I hear these things and I look at this thing. Okay, these are this looks like or sounds like a low-hanging fruits, but then they are very, very critical and crucial. Yes.
Yeah, I
Yeah.
exactly know what you are talking about because same for me when I was starting with hardware design. Uh, my goal was like schematic. Schematic is everything. I have to create the schematic correctly. But
Yes. Yeah.
uh, more and more I was in hardware design, I realized schematic is like super small part of the whole big design process, and you have to consider
Exactly.
so many things and make them right. It's not only about
Yes.
schematic. It's about
Yes.
schematic, PCB, production, components, everything together, manufacturing, like
And there are other, I'd say, it sounds silly as well, right? I'll give you a simple example. Uh, as we were doing, I worked for Marvel, and then we were doing this uh, chip for Chromecast. I'm not sure if you heard about this
yeah,
teeny streaming device. Okay,
yeah.
it's revolutionized the way we watch or stream video content. And okay, we have certain power targets and performance targets. It's all good. Um, but then when we took it to the field, okay, you know the use case it is? People plug it behind their TVs.
Mm-hmm.
And these TVs are wall mounted
Yeah.
and they have really narrow space, not much, say, airflow, right? Now you have this small device hanging in there, okay, like in a narrow cell, okay. We get the complaints that, oh, it's getting heated, right? I was like, what? That we didn't observe that in the lab because lab, you know that, right? So it's okay, it's open space, and even if you connect to the TV, yeah, it's still on your workstation with plenty of airflow around it. Yeah, and if you go back and look, the next generation, the first generation was it's a HDMI plug,
Mm-hmm.
and the next generation it has a small cable.
Mm-hmm.
So it has the HDMI port and then cable that connects to the small device, and
Mm-hmm.
then the device is kind of hanging there.
Mm-hmm.
So that's a simple solution, yeah. So to make it much more, I'd say, environment friendly in the
Yeah,
sense
but I
that
guess
in
when
terms of
you were
airflow, yeah.
simulating and everything, you really didn't thought about everyone is going
Exactly.
to mount it
Yeah,
in this
yeah,
kind of environment. Uh,
that's true. Yeah.
okay, so what do you
Because
have on?
back, yeah,
Yeah,
go ahead.
what do you have on the next slide? Because we are running out of time. We have to.
Yeah, this is so many interesting. That's the on the hazards. That's the last topic. But
Mm-hmm.
then, if I want, I want to talk about a little bit about the designing, if that is of interest.
Yeah,
How
yeah.
we
Okay, so how do you
design.
design chips?
Yes. Okay. Designing. I took a small example. Okay. We can think of a two-way switch that we usually we find in our hallways, or if you have a multi-level house, right, you'll find it in our houses. It's a simple problem, right? You have a bulb in the staircase or a hallway. You're going from one end to the other end. Okay. So when you start, you want to turn on, and then when you reach the other end, you stop it. Okay.
Yeah.
Take the simple case, and then we try to model that. Here, I have a small table.
So we
I
are going
call
to
this
design chip for
as
this. Yeah.
yes.
Okay.
So I'm going to show you, walk you down with the steps and see, okay, it's a small, teeny chip, but then I'll show you. Yeah. And I call here as two columns, which is S down, that means the switch, which is on the downstairs, S up, that's a switch on upstairs, and there's a light bulb. When both switches are in on position, light is on. When both switches are in off position, the light is on. And it's off when one is on, the other one is off, right? Now, if you were to model a circuit for this, okay, um, let's have this small model with the switches. I have 110 volt supply on top, and then there's light connected on the down there with the grounded. In between, I have these switches arranged in series and parallel fashion. I call this switch as A, and this is what we call A bar, which is the opposite of A. That means when A is on, A bar is off. When B is on, B bar is off. When A is off, A bar is on. Okay, and then when B is off, B bar is on. Okay, now take the first condition. When both are on, you have the current flowing through the left side branch, makes your light on. And of course, on the right hand side, they are disconnected. Now take the situation where one switch is on, one switch is off. Now on the left hand side, there is no path for the current to go through. Similarly, on the right hand side, no path for the current to go through. So it's off. So this is the model.
Okay.
Now, our next step, I'm going to replace these switches with an electronic components, which are the transistors. A transistor by itself is nothing but a switch. And so this is how the schematic looks. This is a CMOS schematic. So in CMOS technology, we design a complementary transistors like PMOS and NMOS together. It's not just standalone one transistor. So you will see a pair of transistors here. And so that's why 4 switches now has become 8 transistors, 4 PMOS and 4 NMOS. And you see here, this is A, B, and then A bar, B bar complementary. And then we have this A, B, A, and B organized in a different fashion here. Okay. Okay.
Oh
now
yeah,
we
I
came
see.
from
They
the
are on
problem.
different
Yes.
sides. Oh, on the bottom
Yes.
one, they are same on one side and same on
Yes.
the other side, but on the top one, they are actually.
They're alternating. Yes. Okay. Now we're going to replace this schematic with the layout, which I have shown you earlier, right? Which is basic inverter where we have 2 transistors. Now, this is a 2D format, not a 3D structure, but yeah. You can have this correspondence. You see this 1, 2, 3, 4. 1, 2, 3, 4. So there are 4 transistors on the bottom, 4 transistors on the top, and they are PMOS and NMOS. And in between, you see these, say, patterns of structures. These are the metal connections. So they are connecting different, because the transistor structure is just itself here. It has 3 terminals,
Yeah.
A, and then it's called drain, and then source. So now those are connected together. So this is how you see here. So there is A and B as the input, and then now this input goes to different transistors.
All the A's are connected together.
All the A's are connected. All the B's and B inverts are connected. Yeah. So this is how the layout would be. Now, if you send this to a fab, they manufacture it, and then you put it in a package, and then you get a switch with two terminals, A and B, and then two more terminals for supply.
Mm-hmm.
You can apply uh, 1 volt or something. Yeah. And yes, instead of a light, you can replace that with an LED or a bunch of LEDs. Okay. You don't have to be like 110 volts. Yeah.
So that's
Now
what is on the
this,
next slide.
so what we have on the next slide is, so
Oh
this is a
no, this is
small
this is
example.
different. Okay.
Yeah, this is a small example
Mm-hmm.
that I showed you. But in the next slide, uh, like we've been talking about the designs, the chips can be as complex as we want, right? But of course, we cannot do this or similar approach for large complex chips.
Mm-hmm. You can
So need
basically
to
draw
have a
this
streamlined.
manually.
Yeah, these ones you can draw manually.
Mm-hmm.
But then imagine if you were to draw like a billion transistors manually, forget about it, right? So that's not what we want. We want a streamlined approach where we can do things much faster. So for that, I'm taking a full adder as an example here. It's still not as complex as you see a typical
Processor.
integrated circuit. Yes. With just a full adder is nothing but you're adding 2 bits, A and B. And if you have a carry coming from your neighboring bits,
Mm-hmm.
it's like simple adder, right? Your 1 becomes 1, 0 and 1, okay? And then 0 and 1 becomes 1, sum, and then 0 carry. We have done this basic in our digital courses. Yeah. So what we do is that like the software guys has their high level coding languages like C, Java, or Python. Even for hardware, we have languages called Verilog and VHDL. So we code these languages are purely to code the hardware structures or hardware functionality. The difference would be that at a very high level, it takes C, Java, or any of those languages. The programs you write, they are executed sequentially,
Mm-hmm.
like one block of code executed after the another one.
Mm-hmm.
Where when it comes to hardware, okay, let's take the simple schematic. I cannot say that, okay, I apply a signal for this input A and then wait for it to propagate down and then apply B. I cannot do that because I have to do things parallelly, simultaneous. So the code in our languages, it runs simultaneously.
Mm-hmm.
So if you apply two signals, it processes two signals simultaneously at different timestamps. So that's the basic difference between the software programming languages to hardware programming
Mm-hmm.
languages.
So basically, you describe this physical connection.
Yes, yeah, we describe the physical connection, and we do have tools to convert this high-level language description into a schematic representation. And based on the schematic representation, what I show here on the right-hand side is actually a full chip. It has logic much more than the full adder. But then I try to show you the different components of the chip. So on the periphery, what we call is this input output structures. So they operate at a very higher voltage compared to the logic in the middle. So the logic in the middle is digital logic that can operate at lower voltages like
Mm-hmm.
0.75.
Mm-hmm.
So lower the voltage, it consumes less power. So you have advantage there.
Mm-hmm.
However, now on the periphery, with the signal that we receive from the external world, so we have some dedicated interfaces, and they come with their own voltages like 1.2 volt, 1.8 volts, 3.3 volt signal levels. So we cannot change those things because those are the standards. So these input output structures, they have the structures, they operate at both the voltages. So when they're interfacing with external world, that part of the circuit operates at 3 volts or 2 volts, and then it reads the signal and then connects, I would say, steps down into a digital equivalent of it to a zero point 0.7 volt, 0.75 volt level.
Mm-hmm. I
And
remember. I
then,
remember
yeah,
question From our Discord, someone asked like, why there is this 1 volt power supply on the chip, and
Okay.
that this is exactly the reason, because some parts of the chip may be running on much lower voltages, and
Yes.
we need to power it up
Yeah.
somehow.
And to explain it, right? So now if you remember the power equation, so the power is CV square. So your capacitance into voltage square. Now lower the voltage, you will see a quadratic reduction in the power
Mm-hmm.
requirements. So that's the reason why we want to shrink the devices so that we need less power, and then we could do a lot more for the same power.
Mm-hmm.
If yeah,
Even the heat is all the power will change
yes,
to heat.
yes, exactly, exactly. Yeah. So that's the reason why we would like to lower the voltage. Yeah,
Mm-hmm.
then we get the benefit. I mean, we shrink the feature size because now assume that you have the transistor this big compared to this big. Now, you look from an electrical point of view, from electronics point, electrons point of view. If an electron to reach from one side of the transistor to the other side, it's okay. So it has to travel this distance. Now you have a much smaller transistor. The electron only needs to go from here to here, okay, to establish the connection. So this, the electron reaches from source to destination much faster than compared to what we have a bigger transistor. So your performance is much higher now
Mm-hmm.
for the smaller devices. So that's one way you can increase the performance. And at the same time, you also want to reduce the power. Now, it also requires less power if you lower the voltage. Yeah.
I would like to point out what is different between designing board and designing chips. I think most these complicated chips, they are like almost always auto-routed, correct?
Not just routing, but also the performance, right? Like I
Mm-hmm.
said, yes. I mean, it depends on the functionality. Yeah. So because what we are seeing is, I would say, the tangible components of a chip. So the intangible components is the performance, right? So that's another one. So uh, if I can run this chip at maybe 1 kilohertz or 10 kilohertz, 1 megahertz or 500 megahertz or 1 gigahertz based on how I designed it. Yeah. So the logic needs to be structured so that we can squeeze the maximum performance out of it. Yeah. So the higher the performance you're targeting, okay, the more challenges you face.
Mm-hmm. That's why auto-router is the basically only option which can find out how to place
Yeah.
and
So
connect everything.
exactly right. So say if I want to connect, you see here, you see the thin narrow,
Yeah.
uh, uh, let's say the path here. I can connect it from here to here. Okay. Or I could take this connection, go
Yeah.
around, come back and connect. It depends, right? I can still do that. It is legitimate. And even from the manufacturing point of view, yes, it is acceptable. But the longer the route, it takes more time. It has higher resistance. I cannot operate, or that limits at what performance I could operate this chip.
Mm-hmm. And auto-router would find out like this doesn't meet the
Yes,
specification, so
yes.
and also I guess because there are so many components, it would take years and years and years if it would have to be connected manually.
Well, certainly I agree, but if you were to design, even the tiny chip that I'm showing here by manually drawing these structures, okay, that would be someone's lifetime project, I would say. They might retire. They might retire sooner than they could finish that. Yes. Yeah.
Okay, and then
So.
Kind of a weird question. So why we can use Autorouter designing chips and not on PCBs?
Wait a minute. I believe even
You
PCBs
can
has
use
some
you can
auto
use it on
routers.
PCBs, but it's useless. It's
Oh, is
almost
it?
okay. Some people now will argue like, oh, I use Autorouter all the time. I don't use it because, for example, one of the reasons is I haven't found one which would be a really good one. You can use Autorouter if you have a lot of space. Maybe it will find connections. Uh, is it going to be routed correctly? I'm not 100% sure because I don't think they are so good as cheap Autorouters.
When you say good, are you referring to, is it like 80% good, or it meets 80% of your expectations, 90% of your expectations, or how is that? Because,
So what
yeah, go ahead.
yeah, what I found the biggest problem is uh, routing boards is also about placement, and it means when I do placement, I always think how I'm going to route the specific components. And but auto router it doesn't know. You can set up some rules and tell them like, I don't know, mm, this has to be this distance or something. But auto router starts routing somewhere, and then it will find out, oh, it's not possible to connect it based on your specification.
I see, I see, I see. Um, yeah, talking about the placement, what we call floor planning.
Mm-hmm.
Yes, we do see those challenges sometimes. Uh, in chip designing, auto router, what it does is, okay, there are configuration settings that you could do probably, and then it depends on like, okay, what is the scanning width that it can do when it is routing? Okay, can I scan next 20 tracks, 30 tracks to
Mm-hmm.
see I have a wiggle room or something?
Mm-hmm.
Okay, and we often end up with what tool come back and saying that there are two things, right? One is tool either can give up and then say, hey, there are 100 nets need to be routed. I could only route 70 and then I could not route 30.
Mm-hmm.
That may not be helpful, but what we do is that, no, let's do this. Try to route all of them and then tell me the areas where it is crowded.
Mm-hmm.
Okay, so what we do is usually we go with that option and then say that we let it route what we call the trial routes, and then it come back and says that, hey, these are the areas. I have like 3 tracks available, but looking at the placement of your different components, it happens to have 5 nets that
Mm-hmm.
needs to be routed to that particular area.
Mm-hmm.
So that's what we call the congestion. Now we
Mm-hmm.
go and then we analyze and see, okay, now let's move it to another place or adjust the placement to see if that helps. So we do those trials, and typically our chip designing, it takes roughly about a year and a half or so. And during this process, yes, we do several of these trials and
Mm-hmm.
playing with the different placements and stuff. Yes,
Mm-hmm. So it's
yeah.
not only like hit button and then you
Hit
send it to
button, no,
production.
no, no. I mean, there are several, I would say, people in the industry. They wish they have something like that, but those are the challenges. Yeah, yeah.
Oh, okay. So
I
this
mean,
is.
at a very high level, if you see that, right? I mean, we use I mean, Autorouter is a software. Okay, we can. I mean, the software, any software, right? It performs or it works how it is designed or based on how it is structured. Okay. And fortunately or unfortunately, we cannot feed the context to these softwares. We can only feed the inputs.
Mm-hmm.
And we cannot say that like, hey, I'm designing the Wi-Fi chip so that you need to consider this.
Mm-hmm. So
So we
I
need
think
to
this.
feed that in terms of configurations.
Yeah, I
Yes.
think this is very similar basically to PCB routing. The problem is in PCB auto router, you the auto router doesn't have kind of option to maybe move something, or even in chip design, you have to move it manually, or auto router can.
Yes, we have to move. We
You
have to
have to
move
move it
manually.
manually. Ah.
Yeah, yeah. There were some solutions where it's not widely popular that they claim that it can move, but then the results are not, let's say, as good as
hmm
expected. Yeah.
One of the
Still
re-
preferred is we analyze and then we manually move. Yes.
One of the reasons why I never really invested too much of my time into auto routers is because uh, I did experiment. Like I took fully routed PCB. I removed 4 PCB tracks and asked auto router to finish it, and it was not able to do it. So I just gave up. Like,
I see. I see. Um, Maybe, yeah, maybe if you can spend some time and understand, right? Even the software can tell you or give you the reasons why it could not find. Probably that might help because software. The good thing are about the softwares are like they are configurable
mhm,
and programmable, and most of the times the softwares are developed to address several of those situations or scenarios. Now, which is good, but on the user side, what that means is that, hey, you have so many settings, so many configurations. Okay. Now I need to understand how the software behaves for different
mhm,
set of configurations.
mhm,
And if I know that, if I can program it as per my requirement,
mhm,
I could make good use of the software to achieve the results that yeah, I wish.
So maybe this could be reason because basically in chip design, there is no other way to route chips. You have to use auto
We
routers.
have to,
So
yes,
you
we
have
have
to
to use,
figure it out somehow. But in PCB
right.
design, it's like it didn't work. Okay, let's do it manually.
That's true. That's true, right? Because, yeah, I mean, you well said. I mean, if there is an alternative, we always try to choose the least resistive path. And then, I mean, this happens with most of the experienced engineers out there, right? Because they know one way of achieving result what they want. Do they have patience to invest time on this, okay, new technologies and stuff? I mean, I completely agree, but we do also come across these situations where we have new solutions, new software solutions that come up with, and often we may not see the result with those what we
Mm-hmm.
expect. So it takes several years for us. We need to try, spend some time, okay, investigate, and then work with those
Mm-hmm.
counterparts and try to tune it and understand it, and then make it production worthy.
Mm-hmm. That's
Yeah.
interesting.
But it
Oh,
pays. Yeah, it pays. The effort what we put, right? It really pays. It's worth it. Yeah.
okay. When we are talking about this, there is this AI everywhere,
Hmm.
AI topic,
Yes.
AI auto
Yes.
routers. What's your opinion? Because I've seen one of the very first companies like Cadence a couple of years ago. They were talking about implementing AI to help with chip design, for example. Do you think it's going
Yes.
to help?
Yes, definitely. Yeah. Now, I'll give you very at a very high level. Okay. Uh, I think the topic we just discussed is a good basis. Okay, for this. Um, the fact is, yes, we use the auto routers. Take an example. And Autorouter, if you look inside it, it has several options or several features that needs to be tuned. Okay. And if I go back maybe 10, 15 years ago, the features might be limited. Okay. Maybe for any designer, if they invest time and have patience, at least they could run several trials and then identify for which configuration how the software is behaving,
Mm-hmm.
and for my use case, how can I do that? Or how can I make use of the software, which configuration and settings. Now, over a period of time, we try to shrink the feature sizes. And with that, we have to take care of several factors that influence. the designing of the chips that resulted in a broad spectrum of features and the configuration settings that are needed, right? Which even I would say to a certain extent, even it's a burden for the designers to explore all those options and features. Now, with the AI, what makes it easy is that consider this as a multivariable or multidimensional space, like each setting is a dimension. Okay. Just like in this example, we have two inputs, A and B. It's a two-dimensional space. Right? Now imagine if I have the 10 signals, that becomes a 10-dimensional space. Now, as an engineer, if you were to go and navigate the multidimensional space, try to find out optimal configuration, right? So it is time-consuming process. Even though if you were thrown like hundreds of compute resources at you, still, right? Running different trials, gathering the data, analyzing, and then formulating and detecting insights, right, out of it. So it is an effort, and definitely, AI is a big help there, and it will help to design chips faster, and it will also help to have a better quality, okay, and to also achieve better results in terms of performance or area or power, whichever you are targeting.
But basically, what
Yeah.
you are talking about, it will suggest the circuit, it will kind of analyze it, maybe simulate or something, then
Yes.
it will analyze the results, and
Yes.
then it will learn, like, okay, maybe these results are bad, so I'm not going to use this solution, let's try something else.
Yes. Exactly.
So
Yeah.
it's not only like AI is not only used to decide how exactly route the tracks, but AI is to decide how to design the whole system.
Yeah. It'll give you the options to. Um, However, having said that, can I blindly, okay, feed my inputs to the AI solution and then expect it to come up with a better solution, right? Um, well, there are cases where it might give you multiple options. Say that, hey, these are the best possible options, because inherently, uh, the AI system, the models are built uh, based on the probabilistic um, relevance or approaches, right?
Yeah.
So what it's going to tell you is that, hey, I have option A with 30% chance or 30% probability, option B with 15% probability, option C with 5% probability, and then I have a bunch of other options with much lesser probability. Now, which one you want to go with? So, because this is a good analogy would be that you have a local optima or you have a global optima. Right now, if I'm designing a small portion of the chip and I'm using, by the way, I forgot to tell you, right? Because the chips, unlike the boards, when we design it, we actually break it into partitions. So we break them into small chunks. So we design these chunks and then we put them back to form a chip. Okay. Now, if I am focusing on optimizing a small portion, a chunk of the design, that is what I'm looking for is a local optima. Okay. So now the local optimal solution may not be good when I put it together in a bigger chip. Okay. A simple example would be that, okay, I have the square shape here. Okay. If I give it to AI and then I asked it to, okay, can you skew the aspect ratio and see which one works better? And it might stack up some of those big components. Either it can come up with as a vertical rectangular shape or horizontal rectangular shape. Says that, hey, horizontal rectangular shape might be better for this. Uh, you will see maybe 2% performance improvement. Whether you want the 2% performance improvement or you stick with this rectangular shape so that when you put it in the
Inside
chip,
of package. Yeah.
yeah, you have maybe a 5% area gain. So now it's up to you to as a designer, right? You make a call. Okay. So, but then the AI will get you those options.
Mm-hmm.
As an engineer, if you were to search the space and get the options, might take longer time and might take tedious.
Mm-hmm.
But then AI will help you to get you those options faster, okay, and
Mm-hmm.
maybe more options that you more than what you might
Mm-hmm.
thought.
So you don't have to spend 1 month working on kind of one solution and then find out, oh, this is not what I want.
Exactly. I mean, that's a very good point. Yes, it is.
Okay, what else is important from your slides? Because it's it's almost time to finish.
Yeah.
What did
So
we skip?
I think we covered. It's just the
On
yeah.
introduction, we only skipping. Or what was on the last
Yeah.
slide? Did we go through the last slide? I don't
This
remember
one.
what is on the last one.
This one.
No, I mean last slide.
Oh, last is ESD.
Okay. ESD and up. If you go up, what is there? Up. Oh, there is a graph. Oh,
Oh,
what is
this one.
yeah?
This
What is
one.
this?
Yeah. Okay. So this chart shows like okay, um, it is kind of looking back at right. So the how the integrated circuits have evolved in terms of its density. For the sake of discussion, you take let's say small 100 square silicon area, and if you can go back in time to 1972 or 1974, you could possibly fit around like 5,000 transistors
Mm-hmm.
within that area. If you zoom back, the present day, you could pack close to 50 billion
That's
transistors.
big difference.
Yes. So that is almost like a million. Yeah, it's a million times, right? It's a million times
10
more
million even.
transistors you could, yeah, you could pack. So this chart shows the evolution, and in semiconductor industry, what we call is a Moore's law.
Yeah.
So the Moore's law, what it says is that effectively the transistor density doubles every 2 years.
Mm-hmm.
That means in another way, every process node, the transistor area shrinks by half. So currently the chips are being designed, what we call as a 3 nanometer process node, and the 2 nanometer is coming up, and most of the productions are in 5 nanometer process node and 16 or 12 nanometer process nodes.
But I think there is
When I
a
say
limit, correct? Like we are getting close to the limit.
close to the quantum realm, that's what we call, because you cannot go smaller than the size of an atom.
Yeah.
So that's the limit. And today, if I say 2 nanometer is nothing but 20 angstrom units.
It
So
means
20 angstrom
what
means
like
it's
20 atoms?
20 atoms,
Mm-hmm.
yes. So it's 20 atoms right now we are at. So that's the size of the transistor. Okay, now if you start shrinking it, we have to see when we hit the limit. Okay, so now um, we are very close to the quantum realm. Okay, so that's the limit. And we might also use like a one single atom as a transistor as well. So that's what the news is about. There is already work going on the quantum computers. When we go to the quantum realm, as of today, we are using the electrons within the atom to transmit the signals. When we go to the quantum realm, uh, they want to use the, the electron spin, right? So the spins in one direction, the other direction. Okay, and then there is energy level states there. So the electron in the outermost orbit, it has different energy bands.
Mm-hmm.
So now, if you can hold the atom, or let's say you can hold the electron in a certain energy band, right? You can, and you can sense that, you can read it, and you can control that. Yes, you can definitely have more than one transistor in an atom.
Mm-hmm.
If you have 4 valency electrons in an atom, you can pretty much use them as 4, I'd say, transistors or switches. Yeah.
Okay, I think this is,
So yeah, it's still a long way to go. Yeah.
but I think this is
Don't give
good
up.
good ending
Don't give up
for our
your
video.
hopes. Yes. Yes. Yeah. So don't give up your hopes. Yeah. Um, recently, I think week ago, 2 weeks ago, Google made an announcement
Oh,
that
I read something.
they have a significant breakthrough in terms of noise cancellation, especially for this quantum computing area. Yeah.
Uh, okay, so thank you so much, Archie, for this uh, introduction into chip design. I hope many people find this useful and maybe they'll learn something new.
I hope, yeah, I hope this is informative for your audience. Yeah, and I'm really happy that we are having this conversation, and then I get the opportunity to share my knowledge with wider audience. Um, yeah, I'm also looking forward to see how this goes.
Thank you, Archie, again.
Thank you very much, Robert.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FedEval online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.